In his book, What Mad Pursuit, Francis Crick does an excellent job capturing the essence of what has been our focus in Chem 332, the idea that without understanding molecules, we cannot understand life itself. We want to carry this theme forward in our final section on nucleic acids, where we want to understand the molecular level detail of what goes on, for example, in a process like the one that's shown here, which is the process of DNA replication. You can see the DNA strand in orange, the familiar double helix as this DNA polymerase enzyme, its PDB code 1TAU, is replicating that information that's encoded in the sequence, this three-fingered-like enzyme. You can just imagine how it's twisting its way, corkscrewing its way around the templated strand and copying that information. Well, by the time this series of webcasts are over, we'll understand the organic chemistry, the molecular level details, bonds, and atom changes that take place in this process. Let's begin with an understanding of what are the building blocks in nucleic acids. These are the third type of biopolymers that we've studied. We've looked at the polysaccharides just recently, and before that we looked at the proteins. And so now let's take a look at the building blocks of the nucleic acids, the third type of biopolymers. Nucleic acids are made of repeating units that are called nucleotides, and we can strip them down one level further, take away one portion of that repeating unit, the phosphate portion, and we'll call them nucleosides. Nucleosides consist of a sugar component, which after our discussion of monosaccharides, this should be familiar to us now. It's the sugar ribose, which I'll show you the structure in just a moment. And the nucleoside also consists of a heterocyclic base. So our chemistry of aromatic heterocycles will come to play in just a moment as well. So if we look at the sugar component, it's an aldopentose, it's ribose. I'd invite you to pause the recorder once I finish drawing the structure and make sure you see that this is, as I've drawn it, the beta anomer. So the structure of ribose, this aldopentose, looks like this. And if you would go ahead and convert this into the furanose form that is shown on the left, you will see that the beta anomer has the hydroxyl group pointing up in the same direction as the 4,5 carbon bond. So, having done that, you can also see the difference between the deoxyribose, the repeat unit that belongs in DNA. The 2' hydroxy group is absent, and so you've replaced this that particular position with simply a CH2 group as opposed to a CHOH group. And we're going to learn by the time we're finished with this section on nucleic acids how that small change makes a very huge difference in the stability of these two different polymer chains. And maybe you've wondered what's the difference between DNA and RNA, and by the time this series of webcasts is over, we'll understand how that affects the chemistry of these two different polymers, DNA versus RNA. Well, in the actual structure of the nucleosides, the base is added to this ribose sugar. It's added at the anomeric carbon, and so we have, and this is worth writing down in your notes, an N for nitrogen glycosidic bond. And so the base, as you'll see in just a moment, is attached by a nitrogen atom as opposed to an oxygen atom. So we'll replace this oxygen with a nitrogen atom in this position. And so the N-glycosidic bond is how the base is attached to the ribose unit. So beyond the sugar, the nucleotide, beyond the sugar and the base, the nucleotide adds a 5' phosphate group in the hydroxyl group on the 5' carbon. And so you can see the nucleotide for RNA and the nucleotide for DNA there. And these are the building blocks of the nucleic acids. And so when we put them together, just to show you what the covalent bond chemistry of the nucleic acids is, it's a repeating polymer, and so you can see at the top and at the bottom of this diagram we have continued the structure on. We're only showing a small segment of it. We're only showing 3 repeating units, 3 nucleotide repeating units, and you can see the polymeric backbone is a phosphate sugar backbone that draws, as I'm drawing it through this segment, you can see the covalent linkages that are present. It goes phosphate sugar, and we consider it from the 5' to the 3' direction. We consider the phosphate attached to the 5' direction, and then it exits through the 3' hydroxyl group. You can see that there's a direction then to the backbone. There's clear direction, just like in the polypeptide chain. We could define a backbone direction from the N to C. Well, here we can define a direction from the 5' to the 3'. The phosphate group carries with it a negative charge, and so each repeat unit has a negative charge associated with it, and under physiological pH, the nucleic acid backbone is highly charged. It's going to have a charge at each repeat unit. Now, there's the base that's attached to the 1' position, and I forgot to mention why we call these 1' once the base is attached. Once the base is attached, the dominant numbering goes with the base. The base is going to receive 1, 2, 3, 4, 5 to its atoms, and it's numbered that way, which gives the sugar part primed numbering, so that we can still number the sugars, but now they are going to carry primes since they're going to be the second highest priority listing in the of the molecules. So N-glycosidic bond, it's beta linked, that means it's up, just like that hydroxyl group was linked that you showed before. And then the difference is there's a 2' hydroxyl group that's present in RNA, it's absent in DNA. And often you'll see in biochemistry this sort of abbreviated form, that is, there'll be the phosphate group represented by P, and again we move from the 5' to the 3' direction, and so the indication that the backbone is traversing this same segment of covalent atom or covalently bonded atoms that I drew for you. You can see that we enter the 5', we exit the 3' linked through a phosphate ester, and so on and so forth. And then at the top, which is really at the anomeric carbon, the 1 position, at the top, at each of the anomeric positions, there is the attachment of the base.